So topic 3 and 13 is all about periodicity. And so this one is really focusing on the idea of the elements on the periodic table and how their trends vary and how the relationship between their position on the periodic table affects their reactions and their chemical properties and things like that. And so I'm not going to spend really time talking about valence electrons and energy levels and things like that, because I figure we are hopefully past that point here. But electron configuration, I think with this, you just want to kind of focus on terminology here. So you want to make sure you're giving the IB what they want or what they're asking for. And so when they say electron configuration, you're talking about like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. That's electron configuration. So that's full electron configuration. Whereas noble gas configuration would be AR 4s2 3d5. That would be the difference in those two concepts. And so make sure you're giving the right one, because if they ask for the full and you write noble gas, they're not going to give you credit for it. Okay. So do be wary of that. Alongside that, they might ask for the orbital diagram. And orbital diagram is where you draw the blanks out with the arrows. Now, actually, you know what? I'll just do it like this for now, just to make sure we kind of understand. So the orbital diagram has these half arrows that fill in the orbitals with opposite spin, 2 per orbital max. And when you have more than one orbital in a sublevel, you add 1 to each before you double up. Okay, all those rules apply when you're filling in an orbital diagram. I feel like if the IB asks you this question, they'll have the blanks there already for you, but you'll just be in charge of filling them in, because they want to make it as consistent as possible. So you'll draw those. Okay. Sometimes they call it the box and arrow diagram, because they'll have boxes and you'll have to draw the half arrows to represent all the electrons in there. Right. So there's 3 different kinds of configuration that you might have to show. The reason why I kind of talked about this is there are a couple of exceptions that you need to really be familiar with. And that's chromium and copper. Okay. Chromium and copper move an electron out of the 4s into the 3d so that both sublevels can either be half full or full to increase stability. And so chromium, you would usually think, is AR 4s2 3d4. It becomes AR 4s1 3d5, because the one electron moves over and now the 3d is half full. Cu becomes AR 4s1 3d10. So really key thing, the IB wants to make sure that you know those exceptions to the rule. Okay. And I think the way they exploit this is what they usually do. When I see on the IB test, what they usually do is they ask you about Cu plus 1, because a Cu plus 1 ion loses 1 electron. But you have to remember that every time you remove an electron from a electron configuration, it's from the highest energy level. Okay. And so it's not the last one you fill, it's the highest coefficient. And so copper becomes AR 3d10. And they use that question very often because it requires you to know 2 or 3 different things to get the right answer. 1, you have to know electrons are removed from the highest energy level and not the last one you fill in. 2, you have to know copper is an exception where it's 4s1 3d10. And then 3, you actually have to know copper's original electron configuration, because all the wrong answers here kind of exploit different concepts. So some students might write AR 4s2 3d8 because they don't know the exception rule for copper, and then they just remove from the last sublevel that fills. Or other students will say, oh, I know that it takes out from the first one, the highest energy level, but I don't know the exception, so I write 4s1 3d9. And then some other students will just write coppers because they won't see the charge, and they'll see something like that, 4s1 3d10. And so again, the IB is all about asking questions that are more involved than very basic recall questions, because they don't want to reward students that are just memorizing stuff. They want to reward students that are understanding. And so, and if you have to recall multiple things to apply it, that's a better question that reflects your understanding. So they like to use copper plus as an example, because copper 2 plus, you could stumble across the right answer for the wrong reasons. But copper 1 plus, you can only get it right if every single concept is applied correctly. Okay. Questions about that? Please feel free to ask anything. Just because we're recording doesn't mean I won't take questions. Yes.
The orbital diagram.
Yes, orbital.
One where you're supposed to like vary the heights of it to show the different levels, or do we not?
So Nathan asked about, do we have to vary the heights of the orbitals and stuff like that? Generally, when you're doing it in this form, no, you just do it left to right. But if you're trying to explain like why the electrons like fill in a certain way, and you're trying to diagram using the orbital diagram as an example, it would probably be good to go vertically with it to show that. Hybridization is one of the examples where you want to show the different levels so that they merge into an average energy, equal average energy level orbitals and things like that. But no, generally on the test, it'll just be a straight line across like we've written here. That's a good question. A couple of terms with the groups or sections of the periodic table that you should be familiar with. Alkali metals. We'll talk about the reactions of those later. Halogens, noble gases, transition metals, the lanthanides and actinides. Those are your rare earth metals. Those are the two rows at the bottom. They represent the F sublevel. You're never going to have to go that far in electron configuration. You just have to know that that's what they are composed of. Questions on that? Okay. So our main focus on this whole unit, other than like knowing the general periodic table and electron configuration and stuff like that, is periodic trends. And so essentially, we're talking about what type of relationships there are between elements in the same period or in the same group, and how those properties vary, increasing, decreasing, things like that. And so you want to focus on two major ideas here. And this is what I always tell my students. The explanation for trends is one of two reasons. One reason if it goes in one direction, and one reason if it goes in another direction. And if you know those two explanations, you can apply to every trend that is really useful for this. And so when you go across the periodic table, Okay. So as you go across the periodic table, no matter what row you're on, first row, second row, third row, fourth row, whatever, the energy levels stay the same. Okay. But an increase in protons creates a greater nuclear charge. Okay. And it has to be both these things together that allows you to do that, because technically as you go down a group, you get more protons as well. But because you have more energy levels, the ratio of the protons to the electrons is essentially the same. So it doesn't have as much of an impact there. They'll usually call this effective nuclear charge, which essentially the number of protons pulling on the valence electrons. So if you assume every proton pulls on one valence electron, one electron, then a lot of the inner electrons are kind of canceled out by some of the protons, and the remaining protons are pulling on the valence shell. And so for something like sodium, which is in group 1, you have an effective nuclear charge of 1. If you go to aluminum, it's in group 13, that would be 3, because it has 3 valence electrons and effectively 3 protons pulling on those electrons. Oxygen, actually we'll go with sulfur, is in group 16, so there's effectively nuclear charge of 6. And then chlorine in group 17 is effective nuclear charge of 7, and then argon, which is an 18, has an effective nuclear charge of 8. So as you go across the periodic table, the effective nuclear charge increases for the same energy levels. Now, having said that, potassium, because it's in the same group, still has an effective nuclear charge of 1, because you've added an extra energy level, so that cancels out the additional protons except for the 1 valence electron and the 1 proton pulling on it. So all elements of the same group have the same effective nuclear charge. And so other factors affect it. But what does this increase in protons and greater nuclear charge mean? What it means is a greater attraction for valence electrons. And that will be the connection that you make toward every single trend, whether it's ionization energy, whether it's electron affinity, whether it's electronegativity, whether it's atomic radius. All of those factors really comes down to the interaction between the attraction of the nucleus for the electrons. Right. So as you go across the periodic table, your thought should be same energy levels, increase in nuclear charge, therefore there's a greater attraction for the valence electrons. That's the thing you want to think about. No matter what trend you're talking about, that is what's true about the atomic structures. Questions about that? As you go down a group, you have the same effective nuclear charge, because you have the same number of valence electrons, so therefore you have the same number of protons pulling on those valence electrons. What changes is different energy levels. Okay. Which then means more shielding of nuclear attraction. Because each of those inner shells act as a shield or act as a buffer for the attraction the nucleus is trying to reach out to the valence electrons. So every time you add another inner layer, it reduces the strength of the pull of the proton on the valence electron, okay? Which then weakens the attraction for valence electrons. And those two major concepts are things you apply to every single trend. So I think it's less useful to memorize each trend and its effect, because on the short answer, they're not going to ask you that, because you're going to find out on the data packet that all the values are given to you for all of these trends. So they're never going to ask you what is the trend as you go across the periodic table, because the numbers are in the data table already. They're going to ask you why. And this is where the why comes into play, and you won't get full marks unless you address one of these things fully. Also, I think the mistake that students make a lot is they assume that the similarities are already implied, and so they don't talk about them. But you can only compare things when one thing is different and everything else is constant. And so you have to make sure that in your explanations that you address the same and you address the different, and that's how you can come to a conclusion. So don't assume, oh, they know that they're in the same period, so they must have the same energy levels. No, it's your responsibility to say, I can make this comparison because they have the same energy levels and they have different effective nuclear charges. So you have to address both things, the same and the different. You know, it's kind of like in a different topic, like weak acids versus strong acids, right? Weak acids and strong acids both react with carbonates or metals to produce gas. So that's okay. That's a similarity. The difference is that they disassociate different amounts, or you have the same concentration also, but then they dissociate different amounts. So therefore the rate of the reaction is different. But you can only compare those rates of reaction if the concentrations are the same. Because I could make a high enough concentration weak acid, if left kind of uncontrolled, to react faster than a strong acid, because I could manipulate those concentrations. So that's why the IB questions always say, assuming two unknown acids with the same concentration and the same volume, that eliminates that variable from your discussion. Okay. Questions? Okay. Yeah, Althea. They're in they're in that room, the storage room, in the short cabinet. Okay. Yeah. Yeah. So as you have more layers of inner shells, that buffers the attraction from reaching the outermost shells. And so, yeah, the more rings of inner shells you have, the more shielding. That's kind of a key word here to block the nuclear attraction. And so this applies for all your different trends. For example, the first one is atomic radius, which essentially, again, the radius of an atom. As you go across a period, the radius, as you go across a period, you should think, okay, same energy levels, increased nuclear charge. So that means an increase in attraction. So those concepts all together would make you think, what would happen to the atomic radius as you go across? Based on those kind of bullet points, what would happen to atomic radius as you go across a periodic table? Why? It would decrease. Why? Yeah, the greater the nuclear charge would pull everything in more tightly, so your radius decreases, right? And the way Nathan was thinking about it is the way I want you to think about it. I don't want you to memorize that atomic radius decreases. Like I said, if you look on the data packet, all the numbers for radius are given to you in your data packet. So why would they ask you that? There's no point in them asking that. And so they wouldn't care whether it decreases or increases. They would say, explain why it decreases. And so the part in blue is the more important part. The pink part, you can infer and deduce from your knowledge of the blue part. So stop having to memorize things like that. As you go down a group, you have, the same nuclear charge, but an increase in energy levels, which is an increase in shielding. Okay. So based on that knowledge, what do you expect the radius of an atom to do as you go down a group? Right. It should get bigger. So the radius should increase. You can also put in here electron repulsion. That's not a bad thing. Like as you add more and more electrons, they repel each other more and they want to spread out more. I was thinking about that. You could incorporate that in there as well. But really the fact of just having more energy levels is really the important thing. Questions? Okay. I'm going to be lazy here. Okay. I'll leave it here. The second trend is ionization energy. Okay. And ionization energy is the energy required to remove one electron from, actually we'll say a species in its gaseous state. Oh. Now, the first ionization energy is from an atom. And that's the one we're going to focus on here, because as you lose more and more electrons, things get a little bit more kind of blurry. But the energy required to remove one electron from a species in its gaseous state. And so that would look like something like this. For those of you in higher level, you need to know that reaction because that's part of the Born-Haber cycle. Now, standard level, you still need to know that reaction, but for higher level, you definitely will see that. In standard level, they might ask that as like a 1-mark question or like a multiple choice question. Which of the following reactions represents the first ionization energy of an atom or something like that? So, just copy and paste your notes from the last section and paste them right down here. Okay. You don't have to write it all out again because you're going to, again, we're repeating ourselves a lot. Now that we've defined ionization energy, what really determines whether an ionization energy will be higher or lower? What does it come down to atomically for that? What's the basic kind of idea? What determines how strong the ionization energy is going to be? The attraction, the protons, the attraction it has, right, Aiden? So now it's a matter of, okay, that attraction, is it dependent on how many protons we have, or is it dependent on how many energy levels we have? Because based on where we're going on the periodic trends, it matters. So like Aiden said, across a period, you have the same energy levels, we have more and more protons pulling on those same energy levels. So you have an increase in attraction. So how do you think that will affect the energy it takes to remove an electron? It's going to go up. It's going to increase. Okay. But as you go down a group, what happens to that nuclear attraction? It gets less and less because you have more and more shielding between. So what's it going to say about the energy required to remove that electron? That's what? Decrease, exactly. Because the attraction gets weaker. So therefore it takes less energy to remove the electron. No, it's usually kind of large bursts of energy. So like it's either like electricity or like a laser or something like that, some way to no. Okay, they just like flick it. Yeah, usually it's like bursts of energy, whether light or electrical, I believe. And they do it with like a large amount of it too, right? So like a mole of it, not like just a couple atoms at a time. So like the ionization energy you see on the like periodic table, like that's the energy per mole of electrons lost. So it's a lot. Yeah, Luthia? Find what? They're in the little tow trays. You pull out the tow trays in the short shelf next to the two tall ones. Next to the window.
Oh, okay.
Next to two tall shelves, two tall cabinets. Okay. Sorry, questions about that? I feel like we're moving very quickly right now. Okay. The next one is electronegativity. Okay. Electronegativity is the attraction a nucleus has for a shared pair of electrons. Okay. It is a relative scale. So it's not an actual number like ionization energy is. It's a relative scale to compare between elements relative to, I believe, hydrogen. So it goes from like 0.7 to 4. Okay. Electronegativity itself?
Yeah.
Oh. Okay. I'll make it make sense to you. Okay. Here's what you want to think. Okay. This only works when you're bonded with another atom. Okay. So when you're bonded with another atom, the electrons overlap in between the two atoms, right? And what's holding them together is those electrons in between them. Both nuclei are attracted to those electrons, and that holds the bond together. That's how a bond forms, okay? Now, when you look at an atom's perspective, okay, okay, as you go across a period, if you replace that atom that's bonded to another atom with another element in the same period, okay, and you're going left to right, what's happening to the attraction the nucleus has for that shared pair of electrons? Why? There's more protons with the same energy level. So the distance isn't really changing, but the protons pulling on it are, and that increases electronegativity. Okay. Okay. Yes.
Why is the shared pair of electrons like that?
Because what you're doing here is you're not pulling on your own electrons here. You're pulling on a pair that are shared between you and another atom.
Okay.
So this is why difference in electronegativity tells you what type of bond you have. Because the greater the difference, the greater in pull difference means that one pulls on it more than another. Okay. Now you got that same nucleus, which has effectively the same number of protons, but it's getting bigger and bigger and bigger. How's the attraction for the nucleus now for that shared pair of electrons? It's less attractive because it's further away. Okay, so it would decrease. Okay. So knowing that, okay, what are the characteristics of an atom that would have the lowest electronegativity on the whole periodic table? What would be the characteristics of an atom that would have the lowest electronegativity? Like just not a position, just characteristics. What would you expect the element to have the lowest electronegativity to be? How would you describe it? Exactly. Lowest effective nuclear charge with highest valence shells, highest number of shells, energy shells. So where is that on the periodic table? Bottom left. That's francium. Okay. Now, what type of element would have the highest electronegativity? Describe it. Describe it. Lowest valence shells with highest number of effective nuclear charge, which would be fluorine. Why not neon? Or why not helium? It's got a full, so it can't bond. Exactly. So that's why it goes from francium to fluorine and not the noble gases, because they don't bond, so you can't measure electronegativity. technically the ones down further are large enough that they actually do bond, but that's beside the point. So this is where, let's see, let me pull up my, it's like sorted it out all differently now. Oh, here it is. So this is where that kind of comes into play, because the electronegativity, this is that group 1 effective nuclear charge. So francium would have the lowest electronegativity. Effective nuclear charge is 7, and fluorine would have the highest, because these actually, well, yeah, we'll just say for our purposes here, xenon and radon do bond, but for our purposes here, they do not bond. Yes.
So, which would have like a bigger, like greater electronegativity between like something like oxygen and chlorine?
Right.
One's, like, further out, but
So that's where the IB will never ask you that, because there's not necessarily a trend in here. But I would say this: the energy level generally has a greater impact than the effective nuclear charge, just because one significant energy level increase outweighs an effective nuclear charge increase of 1. Because in reality, oxygen's higher. Like fluorine's 4, oxygen's 3.5, chlorine's 3. So in reality, yes, but the IB will never have you compare diagonals, because again, it's more inconsistent that way. Okay. So you want to think of electronegativity as essentially a tug of war between two nuclei, and whichever one has a great electronegativity wins that tug of war more. So it owns the shared pair of electrons more, so it becomes more negative. And so that's where that difference in electronegativity comes into play. If it's a 0 difference, then they're pulling equally. If it's a little bit different, like 0.6, one's pulling slightly more. But once you get to the big difference of 1.7 and 1.8, the difference is so big that essentially one nuclei wins the tug of war and just takes the electron from the other one. And that's where ionic bonding comes from. So ionic bonding is type of covalent bonding. It's so imbalanced that you effectively have ownership of the electrons on one atom versus the other. Okay. Does that electronegativity make sense now? Okay. Questions? Electron affinity. Okay. Electron affinity is a weird one. It does still follow the general trends, but there's some really weird exceptions here and there. Actually, yeah, we'll talk about like other exceptions on ionization energy later on when we talk about graphs and stuff like that. But electron affinity is the energy released when a species gains an electron. So usually when atoms gain electrons, they become more stable, closer to a filled sublevel or an energy level. So therefore, they release energy because they're becoming more stable, and that means they can exert less energy to exist. And so you'd see something like, in a gaseous state. Sorry. Can't forget that. It is the most important part. You would look like this. This looks kind of different. I wouldn't say it's the opposite of ionization energy, because it's not like the reverse of the reaction. It's actually gaining the reaction from the neutral to a negative. And so I'll be honest with you, like the idea is, yes, electron affinity increases as you go across, and as you go down, it decreases, just like the other trends. But I think with this, the big thing is, now one for higher level, yes, you have to use it for the Bohren-Haber cycle again. But I think the key thing here with electron affinity is, why do elements like nitrogen not have an electron affinity. Okay, so when you start running into the issues of why are there exceptions to trends and why are there lacking numbers and stuff like that, that comes down to electronic structure. That comes down to electron configuration. So if you ever get stuck on trying to explain an exception, draw out the electron configuration and see if that helps you, because that would, or the orbital diagram, that should help you. Okay.
The thing that's like, it's already has
Right.
things that it doesn't want to.
Exactly. So like Nathan said, when you draw out nitrogen, you go 1s2, 2s2, 2p3. So it looks like this, where you already have a half full sublevel. So adding an electron to that actually increases the repulsion so much, it becomes more unstable. So there's no benefit for nitrogen to do that. So therefore, that's why you see nitrogen not having an electron affinity listed on your periodic table. Are you looking for something, Erica? Yeah.
Wanted to use this idea initially, but decided not to. You don't have like, you have a lot of important south Philly. Idiot again? Idiot. Last time you.
Oh, it must be the heat. Okay. Questions on that? Okay. Now, ionic radius. Yeah, go ahead. Ionic radius isn't really a trend. I find it's kind of weird. Well, it is a trend, but in a different sense. Okay. Ionic radius is a trend in the idea that when you're comparing ions of different elements and how they kind of behave with each other, you have to compare them as isoelectronic ions. Isoelectronic, actually, you won't even write ions, just isoelectronic species. Okay. Isoelectronic, when you break it down into two parts, electronic is electron. Iso means the same, like the word isosceles triangle, right? The word isotherm or isobar or something like that. That don't mix up with isolated. That's a different, like that's from soul, which is like individual. But iso in there is constant. Okay, isotope, right? Same protons. So isoelectronic species means same number of electrons. And so generally when you're comparing ionic radii, you're either comparing ions or species that have the same electrons, or you're comparing an atom versus its ion. Those are really the only two. And so what you'll see is something like Mg2 plus, O2 minus, F minus, Na plus, and like Ne. Wait, is that the same? Yeah, okay. So they'll say rank the like order these in size from smallest to largest. Okay. And whenever you're trying to do this with ions, I always do this. I always write out how many protons and how many electrons each one has. Okay. So protons and electrons. Well, electrons, protons, Mg has 12, oxygen has 8, fluorine has 9, sodium has 11, and Ne has 10. Therefore, Mg2 plus has 10 electrons, O has 10 electrons, F has 10 electrons, Na has 10, and Ne has 10. Okay. So what's your determining factor in this size comparison? What's the determining factor? What's going to differentiate them? What aspect of these ions is it going to number of protons? Because what's that going to mean for you when you have more protons? Atomic radius is smaller because there's greater attraction, right? So if you're going to order this, you're going to say the smallest one is what? The one with the most protons. And then the next one, and then the next one, and then the next one, and the next one. So O2 minus is the largest one because it has the fewest protons to pull on the same number of electrons. And those electrons will repel more and they'll spread out more. Now, if you have one that's a higher energy level, that one by default wins. So like if you have like one that has 18 electrons, that one's always gonna be the biggest one, no matter what. It has another shell. Yeah. Was that your question? What was your question? Yeah.
So you said that you could also do it with an atom and its own ion.
Yeah.
How do they have the same number of electrons?
They don't. So they have the same number of protons. So then you're comparing. Yeah, exactly. So that's where I kind of hear whenever you're trying to figure out, like, whenever you're comparing atoms or ions and stuff like that, I think it's important to identify the protons and electrons. Because even if you don't know what you're doing, if you write that out, the number of protons and electrons, you might see something that's different or something that's the same, and that might help you figure out the problem. Okay. Instead of memorizing, oh, the cation smaller than the atom or the anions larger than the atom, stop wasting space on memorizing trivial details. Those things you can always figure out if you just go, if I'm comparing ions, let me just look at the number of protons and electrons and see what's the same and what's different, and that should be able to help me. Minimize what you have to memorize. But like what Nathan was asking is, like, let's say you look at Na versus Na plus. Well, they both have the same number of electrons, protons, excuse me, but one has 10 electrons and one has 11 electrons. Okay. So which one's going to be bigger? Which of these two species is going to be bigger, Na or Na plus? Na. Okay, why, Aiden? It has more electrons, and more significantly, it also has an additional what compared to Na plus? Yeah, but where's that electron? On the next shell, right? So there's an additional shell there as well in this. So therefore, Na is going to be bigger because it has 3 shells or energy levels versus 2. Now, if you compare fluorine versus fluoride, it's 9 and 9 and 10. Okay. So which one's going to be bigger? Fluoride. But that's not because it has more shells. It's because it has more electrons, which causes more repulsion. So when the electrons have more repulsion, they spread out more because the protons are unable to hold them together as well. Does that make sense?
Yeah, I was going to ask why it's not a shell. I remember fluorine is not the last thing.
Correct. Yes. Fluorine can afford to gain one more electron before it reaches octet. Okay. Questions on that? Okay. Metallic behavior and periodic trends. Okay. Metallic behavior means to lose electrons. Essentially, that's what really metallic behavior means, because metals lose electrons. Okay. So which trend would most closely be related to how metallic an element could be? Which of the trends? Ionization energy. Yeah. So what you look at is ionization energy. Okay. What kind of ionization energy do you want for it to be more like a metal? Low, exactly, Aiden. So you want a low ionization energy. You want a low ionization energy to become more metallic. Okay. Conversely, non-metal behavior is where you want to gain electrons. So guess which trend that is? Electron affinity. So again, but in this case, you want a high electron affinity because you want to gain electrons. So you want the atom that can gain electrons the best. Oh, we still have a bit more to cover. I'm hoping SL we finish by 10:30 because there's a lot to kind of explain in here. But then I still think HL would finish within like 30 minutes because there's not a lot of stuff we have to talk about in here. Okay. Explaining charts of trends and reading charts of trends, okay? The IB likes to, on the multiple choice, like will show this is a chart of a periodic trend. Which trend is it? And things like that. So like what they'll do is they'll show something. I don't know if I have a copy of this. I may have to go take it from one of my diagrams. Hold on a second. Let's see. Do I have it here?
Wait, this is Tom.
Yes.
Sorry, for electron affinity, you said a higher electron affinity would make it less metallic.
No, more non-metallic.
More now.
Yeah, more non-metallic. Correct. Yeah, it's kind of the opposite. Do I not have my? Oh, darn it. Okay, hold on. Let me pull up my. You don't do it per se, but you still need to understand it still relates to it losing electrons and things like that. And so it's losing the second electron, which shifts it on the trend because now the one that's losing from the full shell is like the one that one lost from its first one from its outermost shell last time. So it kind of shifts everything one over. Okay. Let me see if I have the trend. Where's my trend graph? Ah, here it is. Okay. I wonder if I can just add. Let's see, export, notability. Okay. Come on. Give it a second. Because I want to show you these graphs because they do show up a lot. And you may not be able to tell which one's which unless you kind of look for certain things. Huh? Yeah, I got to be big brained. Wish my iPad was big brained right now. It still says. I don't know if it's just a big file because it's like, or it's just our Wi-Fi being stupid.
I'm not using any bandwidth.
Yeah. I wasn't going to say. Oh,
Dude, it doesn't make
it doesn't.
Aiden wasn't really watching. Like it was,
What is going on?
no, no.
Oh, here it goes. Perfect. Oh, it's like a new. Okay. Okay. Wait, did I add both pages? Wait, where did it didn't add both pages? Didn't I have? Wait, did it? It didn't add both pages. That's weird. Oh, wait, no, yeah, it did. It's just not scrolling down, I guess. Oh, it added it twice because I'm so smart. Okay. Actually, wait, no, hold on. I like that one better than this one. Wait. trying to figure out which one I like better. Okay, this one is the same. I think it's still loading. I think that's why. Okay. So this is atomic radius versus atomic number. And you'll notice that in here that there are certain kind of things that you should be looking for. The first two elements here, that's hydrogen and helium. And then you'll notice that element 3 and then element 10 and element 18. Oh, sorry. I can't do math there. 11 and 19, because that's in the same group, because you add 8, not 7. They're the highest one. And that's your lithium, sodium, and potassium. And then it decreases as you go across. And so that shows you that you're gaining an energy level each time it spikes back up, and then it slowly decreases over time across the period. And so you're looking for these kind of variations here to explain that. Melting point really has no trend. There's no trend for melting point, other than the fact that metals have high melting points and most non-metals have low melting points. So therefore, you see this kind of drastic change between sections of the periodic table. Now, ionization energy is an interesting one because you'll notice that, and this is first ionization energy, I should say, okay? When you think about the periodic table, the first ionization energy of every element, which one should be the highest? Which element should have the highest first ionization energy level? The noble gases, the ones that end the full octet. So that's number 2. Yeah, 2, 10, and 18. The dots don't work really well here, but you'll notice that the highest values here are the noble gases, and that means that it must be ionization energy here because it goes down from there down to the next energy level. It's really easy to lose, and then it kind of works its way back up. So it increases as you go across. Now, having said that, there are a couple of exceptions here and here, which is beryllium and, oxygen. Okay.
Those are the ones with the thing that we talked about.
Huh?
Those are the ones with the thing that we talked about earlier.
Well, yeah, it has to do with orbitals, right? Because if you look at beryllium, it's 1s2, 2s2, 2p1. Okay. So what's the benefit? Why would beryllium have an easier time losing an electron than boron? Sorry, not beryllium, boron. I'm sorry. I had them backwards. Boron. Beryllium, which is 1s2, 2s2. Okay. Why would it be easier to lose an electron in boron than it is beryllium?
Why is it easier in boron?
Yes.
Yeah.
It's the emptying the sublevel, right, Aiden? It's emptying the sublevel, so it actually makes a more significant, it's easier to lose that because you're minimizing repulsion significantly. So boron has a slightly lower ionization energy because you're emptying a sublevel when you do that, versus beryllium, which already has a full sublevel, so you're just breaking it up in half. Oxygen, same idea. Nitrogen, 1s2, 2s2, 2p3, versus oxygen, 1s2, 2s2. Okay. Yes, Nathan.
I thought it was like if it had its own sublevel, then it was harder. Is that not?
No, because anytime you add a sublevel just for one electron, that creates a much more unstable atom.
Oh.
Because there's so much more repulsion, and your nucleus is having to do more work to maintain the atom structure.
Why don't we like draw the sublevel? You know, like we just need 2 and then 8, 8, 8. Like why wouldn't we draw?
Like in the structure itself,
Yeah.
it's too hard to draw it because if you actually drew the shapes of it and all the overlaps and stuff like that, it'd probably be pretty confusing. Like because the s orbitals, the p orbitals look very different, and so when we're just trying to draw the electrons in each shell, we simplify it that way. But if we really want to represent it, we represent it in the orbital diagram. That's the best way to show it. Okay, and so oxygen losing this electron here makes it half filled. So therefore, you can see that it makes it easier, and so that you see a dip in the electrical ionization energy. Also, you could argue that Nitrogen losing this electron would be very difficult because it's half filled. So those two things together factor into that having that dip there. Okay. Questions about that? This also explains the energy levels of like how we use ionization energy to prove the existence of energy levels, right? Because we showed this giant spike here represents a change in energy level, okay? So if you're at any atom that's not at the giant spike, let's say you are here, okay? That's carbon, okay? If you kept doing ionization energy losses for the carbon and you recorded those values, when would the value spike up? Like when would, after losing which electron, would the value spike up significantly? So think about carbon as 1s2, 2s2, 2p2. When would be the biggest jump in difference in ionization energy there between which electrons?
Second to third ionization energy.
Hey, there is a jump there, Alejandro, but there's an even more drastic jump somewhere. The fourth and fifth one, Aiden, right? Because here there's 4 valence electrons here. So the fifth one would be on another energy level further inside than the first 4. Like this jump right here is the biggest. So if I give you values of ionization energy of one atom and consecutive ionization energy, first, second, third, fourth, and fifth, where the biggest jump happens tells you where the valence electrons stop being lost. Does that make sense? Let me show you a chart for that. Let me skip down here and I'll show you a chart because I have a chart of this that I think is pretty good to represent this. So this shows all of the ionization energies for the first like 20 atoms. This is a good reference chart here. Okay. So if you see carbon, 1, 2, 3, 4, huge jump. Okay. You see boron, 1, 2, 3, huge jump. And so all those electrons before the huge jump are your valence electrons.
So for like sodium,
Yeah.
the first electron will move it down.
Yes.
But then it's the next one.
Yeah. So the jump between the increase from first to second would tell you there's only one valence electron. Yeah. So it's the energy of the one after the last one you lose.
For sodium, it's the first one you're removing the last one on that.
Right. 3s1. Exactly. So then you see that jump here is the biggest jump. Okay. And also you prove, so there you prove the existence of valence electrons, but you can also prove the existence of energy levels because you'll notice that if you look at the first, ionization energy, where do they jump up? Helium, or jump down, I should say. Neon, and then argon. So that's period 1, period 2, period 3, and period 4. So ionization energies tell you a lot, told scientists a lot about how electrons were distributed in energy levels because of the difference, the change in the amount of energy it took to achieve such things. And the very popular question here is they'll say like an unknown element in period 3 has the following ionization energies, like such this, this, and this, and this. And then they're like, suggest a possible identity for the electron, I mean, the atom. Well, you look at how many valence electrons it has, and then that will take you straight on the periodic table to what it has. And so if you saw something like, I don't know, something like this, these numbers here, you'd say, well, 1, 2, 3, and then there's a huge jump. So that tells you is my unknown element has 3 valence electrons, so it must be aluminum. Okay. So this table is really useful as a reference. Questions about that? Okay. electronegativity, you'll notice that there are gaps in electronegativity, right? What elements are making up the gaps in electronegativity? Which elements are missing from the electronegativity graph? The noble gases, right, Aiden? Right? Because remember, electronegativity has to be with bonding. So in this graph, you're missing the noble gases. So if you see a chart where like all the noble gases have gaps in the chart, that probably should tell you it's electronegativity. No, you see down there, the 2 is missing. That's yeah, it just doesn't have it. So that's 1 and 3. Sorry, yeah, I don't like the way this is connected because I should have left a blank there, but it automatically connects the lines of the scatter plot. So be familiar with this because the IB likes to ask multiple choice questions about this, standard level or higher level. Look at this graph. Tell me which trend it's representing. Nathan, what's up?
Oh, wait, so the blanks.
The blanks down here don't have points.
The blanks and the lines are actually the points.
Yes. No. Yeah. For some reason, it's not transferring right. So you want to think of this as this.
Yeah. Yeah. I was just looking at it and I'm like, there aren't that many.
And the noble gases are missing here. Oh yeah, no. Sorry. Sorry. Those aren't gaps. These are the gaps here, the missing noble gases. There's no number, there's no value in there. Okay. So that's the kind of idea with that. Okay. Questions about that? Oof, man. Getting too old for this. Okay. I'm just going to demand to teach only 10th grade next year. I'm just going to do it. I'm just going to look. I'm done with IB. Give me easy mode. I'm ready to coast into the second half of my career. Huh?
That's from the movie, is it not?
What? Oh yeah. That's Lethal Weapon.
Lethal Weapon.
Yeah. No. Hey, what's up, Jaden? It's no. Hold on. Danny Glover. Danny Glover and Mel Gibson. He goes, "I'm too old for this."
That's such a good movie.
Yeah.
I love that movie.
Okay. I am still recording though, Nathan. Nathan, I'm still recording. Okay. All right. I shouldn't have maybe threatened to teach only 10th grade next year on this video, but whatever. Okay. So there goes my bargaining chip. Okay. Other things we need to know. Okay. Reactions now. Okay. And so this is going to be a table that we're going to build kind of all the way across. And so let me write out a little bit first, and then you can go ahead and kind of follow along. So period 3 oxides have trends in their reactivity and their chemical and physical properties. And so you'll have major ones here, like Na2O, MgO, Al2O3, SiO2. Let's see, where am I here? P4O10, SO3 or SO2/SO3, and then like Cl2O. Okay. And there are major characteristics that do follow these ideas. And so one of them is pH in solution. So when you dissolve these things, you'll get certain solutions. These two form basic solutions. Actually, you know what? Let me do this and then draw a line here. Al2O3 is amphiprotic, meaning it can act as an acid or a base. And then from there on, they're all acidic. Oh, stretching. No, it's okay. So acidic. So pH in solution, Na2O and MgO form basic solutions. Al2O3 is amphiprotic. It's kind of neutral. And then the rest of them going to the right, the non-metal oxides are acidic. Now, there are a couple of reactions you need to know. Na2O plus water makes NaOH. That kind of verifies the fact that it's basic. And MgO plus water makes MgOH2. P4O10 with water makes phosphoric acid. And SO3 plus water makes sulfuric. And SO2 with water makes sulfurous. So you do need to know those reactions to justify those. Like they may ask you in a question, identify the trend of pH in metal oxides or in oxides, period 3 oxides in water, and then state the reaction for Na2O with water and P4O10 with water. So it could be that could be a very valid question. Okay. Bonding. Ionic. Giant covalent, which is SiO2. And then covalent the rest of the way. I guess if you haven't started writing yet, you could probably start writing now. I've kind of committed to this format for this. There are a couple more things, and then I'll take a step back for a second and let you all copy this stuff down if you haven't started copying yet. Okay. Conductivity. Okay. These aqueous, liquid, or a gas, not solid, because you have the fixed ions. Okay. And for SiO2, moving on, it's never conductive. Okay. I'll give you a minute to copy that down for those of you that just started copying. Be right back.
Where this is from? I think I'm gonna. Well, what made it?
I had one, but my data was bad, but I'm just gonna keep the one I had, not do the new one.
I
The
get
new
my-
one
How good are
is-
you at 10?
What?
How good are you at 10?
Get it.
Like on the spot, can you make up a new server right now?
Well, no, I just like changed my initial experiment a little bit and proposed it to Mr. Trump. He was like, that's pretty simple. I'm like, yeah, you know what, you're right, I'm just gonna keep the old one. The old one just
Is
didn't
it
work.
pretty simple?
Chemistry just hates
Do you
me.
think it'd be okay to do like, the energy from going oxide to conduction?
Yeah, it's dangerous.
It's dangerous.
Explosions.
Where would you put it in?
Is there Sean here?
Jaden.
What's cooking?
You went to go check on something.
So do you think that'd be okay to do?
Dude, you look like you literally just walked off the street.
What do you mean?
Did you sleep outside today?
I said with your mom.
Do you do glasses?
No.
Look nerdy.
Than
I
usual.
have a question. So for my menstruation, the second I put any NaOH, the beneficial
So,
That's the problem. Your sodium hydroxide applied to high molarity. And then dilute it down.
Okay, so if I dilute it point, it's currently 1 molar. So then put it at 0.5.
this guy's literally
Well, if it turns immediately after 1 drop, that means if you have it, it's going to turn after 2 drops. So maybe you want to do like a 10. No problem. I mean, like that's what I would do.
Thank you.
Yeah.
Yeah.
Can I do heat energy for burning alcohol?
Didn't I just say in class, don't do that?
No.
Yeah, combustion, like, no, don't do calorific combustions. Sorry. They're just really bad. Yeah. Cal.
Do you think in
All right. Questions about this chart? Anything that y'all don't understand on here? Okay, last SL thing, and then we'll take a 5 or 10 minute break, and then we'll do higher level. Okay. Again, I don't think higher level will take that long. Okay. So, predict and balance the reaction of alkali metals with water, alkali metals with halogens, and halogens with halide ions. And so, the alkali metals with water. Okay. Alkali metals with water form the alkali solution, which means like it will produce a hydroxide and H2 gas as a byproduct. Okay. Okay. And we usually, when you put in water with sodium or potassium, it'll start to ignite. Like the hydrogen gas will actually ignite. It's so exothermic, you'll see a little fire above the actual metal. I guess you're not going to learn it then. Okay. Alkali metals with halogens. So with this, essentially all you're showing is a synthesis of the halogens here. So you're combining a halogen with an alkali metal to form a salt. Sodium chloride in this case. Yeah, synthesis. The last one is halogens with halides, halide ions, meaning the ion form of the halogen. Now, you have to remember here, though, that this only happens if the halogen that's by itself is more reactive than the halogen that's in the compound already. So fluorine will replace everything, but iodine will replace nothing. And you could also write this as F2 plus Cl minus yields F minus plus Cl2, because effectively that's all it's changing. The Na is actually not changing. So the IB could write it either way for that type of reaction. Okay. Questions about that? Okay. That is the end of SL material. We're going to take a 5-10 minute break. We'll probably say about 10:40, 10:41, we'll resume. I'm going to pause the recording right now. So if you have any questions and you don't want to ask them on the recording, then I'm more than happy to do that right now. But I'm going to also take a little break as well. So I'm going to pause the recording now. And when I unpause it, the video should continue. All right. Bye, SL. Okay.
Yeah, no, well, I understood the video.
Okay.
Yeah.
That's a good point.
Why did you say
Okay.
I want to test out having HL tests. That's all I want.
What?
Transition metals. Bye, Nathan. Okay. Here's the major things about transition metals that you need to know. Transition elements, I should say. Okay.
At least I don't have to worry about that.
All right. They have the characteristics of transition elements. You need to know these kind of characteristics. They have various oxidation states. They form complex ions with ligands. Okay, let's see. Okay. They form colored compounds. And they have catalytic properties and magnetic properties. Okay. The main ones we'll focus on here are probably these first three here. Okay. Because the catalytic and metallic properties kind of are just well, we will talk about them a little bit, but they're more kind of a connection back to the various oxidation states and things like that. And that's how you explain that. But so, yeah. Tall cabinet on the right in that side, that stock room. Okay. So one thing. So various oxidation states first. Okay. Zinc is not a transition element, because it lacks, when you look at this, you look at AR 4s2 3d10, when you lose these electrons and it becomes Zn2 plus, does not have an incomplete D sublevel. Okay. So therefore, it can't have colored compounds. It can't have these properties because all these transition elements are reliant on the fact that there is empty space in some of these d orbitals for electrons to move around. So zinc is not a transition element, even though it's in that section of the periodic table. So kind of one of the other things is that the transition element has to have an incomplete d orbital. D orbitals or d sublevel. Oh, sorry, let me scroll up. Now, all transition elements have a +2 oxidation number. So because of that 4s2 that they lose. So every transition element has at least a +2. Now, all the other ones, it can vary based on the element. Okay. And luckily for you, on your IB exam, on your data packet, they list all the possible the variable oxidation states for every transition element. And so you don't have to memorize them.
Is silver technically a transition metal or no?
I would say no, because it only has one oxidation number, really. Silver 2+ doesn't exist. But you have to remember here, Alejandro, we are only talking about the first row of the D block. So silver would not count in that.
Okay.
Yeah, the properties kind of get a little more difficult in the next rows and things like that. So this is only the first row of D block elements. So that's scandium all the way across to, well, I guess copper, because zinc doesn't count. See, I'm trying to. So how do transition metals form various oxidation states? Okay, so it has to do with ionization energy, because when you start looking at your electron configuration, you'll see different points in which it makes sense for an element to lose electrons. For example, iron is Ar 4s2 3d6. So it makes sense to be a 2+ because you lose the 4s. Okay. But what else could be a reasonable oxidation number for iron based on this electron, this orbital diagram? What other oxidation number could be reasonable?
3+.
3+ or +3, right, Alejandro? Why +3, Alejandro?
Because you could pretty easily lose one more electron from
Exactly.
3.
So you'll notice that when you look at the ionization energies of iron, you'll see kind of a low, kind of dips on that 4s2 and then that 3d6 electron that's lost third. So this one's lost third, and then it has a half-filled sublevel, so it actually kind of causes iron to be able to have that oxidation state. So losing electrons in a certain order allows it to do that. So the 4s is by default, but then you can look at how you would lose 3d electrons to see where the possible oxidation numbers might occur. Questions about that? Complex ion formation, okay? The complex ion formation has to do with the transition element ion and a ligand. And if you remember from organic and maybe from last year, a ligand is an electron, it can be an electron pair donor because it has a free electron pair, okay, which makes it a Lewis base to kind of tie back into topic 8 and 18. A transition element ion is a cation, so it loses electrons, so it's an electron pair acceptor, which makes it a Lewis acid. And so this ligand with its electron pair forms a coordinate covalent bond. Remember, coordinate covalent bond means that one species donates both electrons. So one species donates both electrons to forming the bond. It's, for example, like if you had this. Because the Cl's, the chlorides, have the electrons, and so what you'd see is a Cu in the middle, and the Cl's bonding like this. And this arrow here kind of identifies a coordinate covalent bond. So when you put an arrow on a covalent bond, it shows its coordinate, or dative is another term for it. And the total charge is the sum of the charges. So they might ask you, what's the oxidation number on the metal in this complex ion? And so you'd have to know what the ligand is and know what the charge of the ligand is, and then determine what the charge of the ion is based on that. For example, you might have something like this. Fe, or actually probably 6, if I'm being honest, 6 here. FeNH3 6 3 plus. Well, what's the charge on NH3? What's the charge on NH3?
1.
Nope.
0.
0. Okay. So it is 0. NH4 is +1. So if there's 6 zeros and then 1 Fe, then Fe must have an oxidation number of +3 here. So again, it's just kind of arithmetic here. Now they can try to make it more complicated. Like they'll do something like K3 Fe CN6 or something like this. But again, potassium is +1 plus Fe. Cn is actually -1, so that's 6 times -1 equals 0. So then Fe still has to be +3 here. So they do want you to be able to calculate the total charge or the charge of an independent ion in there. You're just adding all the charges of the ligands and the transition metal together. Questions on that? Now, really quickly about magnetism. Okay. Magnetism occurs due to unpaired electrons. Okay. When they're unpaired electrons, that means there's electrons that are generating fields that are not canceled out by other electrons in the structure. And so that's what causes a magnetic field. And so this is called paramagnetism. And so anything with unpaired electrons cause magnetic properties. Okay. So any transition element has unpaired electrons, therefore they will be magnetic. Also, another reason why zinc is not a transition element, because it doesn't have magnetic properties, because it's completely full. So there's no field. last thing we're going to talk about here is colored complexes. And so why complexes have colors and things like that. Okay. So color compounds / complex ions. Okay. What you need to really understand here is that d orbitals in an isolated atom have the same energy. Just like every p orbital has the same energy in a sublevel, they're the same. But when in a complex ion, the ligands cause repulsion, which changes the energy of the d orbitals into two levels, two energies. Okay. So they split into two different energies. So instead of going from 1, 2, 3, 4, 5, it becomes like this. It becomes this differentiation of split d sublevels here. And it could be 3, 2, it could be 2, 3, either way, depending on the element. Okay. So what happens here is those electrons that are in here end up getting placed into these new split d sublevel. And now what happens is when light comes in, some of the colors are absorbed so that the electrons can jump up. And then the light that's not absorbed is what you see. Okay. So whatever light's absorbed, you see the complementary color of that. Okay. There is no light being emitted or produced. None of that. You need to shine light on it so that you can see the actual color being produced. So there's no emission of light. It's not like in topic 2 where you energize an atom and it like a flame test and it gives off light. This is not that case. This is these ions can absorb light, and they do absorb certain frequencies of light, and they release other ones, and that's the ones you see. So this is that color wheel coming into play here. So complementary colors are across from each other. So if you absorb red, you'll see green. Okay. Questions so far? The split is dependent on 3 factors. Okay. 1, the metal ion identity. So like copper versus iron, they'll have different possible colors. 2, also the oxidation number of the metal ion. So a +2 versus +3 can cause differences as well. And 3, the identity of the ligand, which can cause more or less repulsion. meaning that the D sublevel splits further apart, which means it absorbs higher energy light, or it can get it's closer together and absorbs lower energy light. Don't forget, red is the lowest energy light and violet is the highest in regards of energy. So if you're absorbing violet, that's the largest split between two D sublevels. And if you're absorbing red, it's the shortest split between two D sublevels. Now on the data packet, you'll see a list of ligands in order. I hope I have this. I'm going to have to go find it from somewhere else. Don't think I have it on here. Which packet would I have put it on? Oh, I'd have to go back here. It's topic 3. Yeah.
Is it normal for them to have a hole in here?
Yeah, it helps drain the water out and stuff like that.
Okay.
But no, that was man-made. Let me pull up topic 3 here. I was gonna. Oh, here it is. Okay. So what you'll see here is a spectrophotochemical series. And so here it ranks how strong the ligand is and how far the difference it is. And so this would be the highest difference, and this would be the lowest difference. So you can kind of see what kind of color might be absorbed based on the split. So I minus would have the least effect on it, so it'd be the narrowest split, so it absorbs the lowest energy of light. Cyanide or ammonia or carbon monoxide creates a widest split, so therefore you'd absorb the highest energy color and you'd see a complementary color of that. So you do want to kind of understand that. Like, I don't think they would ask you to predict the color, but they might say compare the energy of the colors absorbed between chloride and hydroxide. Well, you'd say, well, hydroxide has a higher energy difference, so it absorb a higher energy color than Cl minus would. I don't think they'd actually ask you for a color. It'd just be relative to each other. And just comparing there, because they don't actually tell you what color it absorbs. Because it really does depend on the metal and things like that. So it'd be more about how much does it split it. That's essentially it for higher level. Not very much, to be honest with you. I mean, there is some information here, but it's not a huge amount compared to other topics. I just thought about this. What I may do is I may also put up a link to my 11th grade notes in previous years, because I do still have them available. It's been a while since I taught 11th grade, but I still have, the notes are still applicable. And so I will try to remember to put up a link on Schoology so you can have access to my 11th grade notes as well. So that would be topics 1 through 8, I believe. Yeah, because usually we'd get through topic 8 in my 11th grade year. And so all of this stuff is available to you too. I had 3 sections, so it doesn't matter which section you go to, but you can access my notes, and you could, if you want a more detailed version of these notes, you go through here and you could see all the stuff that we were talking about with these trends and stuff like that, and more detailed about each of these concepts and kind of how we're looking at this and stuff like that. So yeah, this goes in a little more detail, but I'll give you a link to that so y'all can have access and reference that as well to study from. Okay. Any questions?
Is Hund's rule and like Pauli's principle part of this chapter or no?
It is in electron configuration, but you're actually not required to know the names of those people. You're only just supposed to know the patterns themselves, Alejandro. So they should never ask you what's Pauli exclusion principle or what's Hund's rule. They would just ask you which of these is an incorrect orbital diagram based on like the rules, right? So you would never have to say, oh, it's Hund's rule. You would say there can only be like one electron in each orbital before you double up or something like that.
Okay, thank you.
Good question. All right. That's it for today. Thank you so much for those of you that were able to attend, and I'm going to stop recording now, and then I'll take any more questions that you can ask off recording as well. All right. Have a good day, y'all.